Alright guys, today we're going to be talking about linear approximations and differentials. The tangent line to a curve gives us a useful way to approximate a value on the curve. We usually write our tangent line equations in point-slope form. Y minus y1 is equal to m times x minus x1 for a particular value of x1 named a. We could rewrite that equation to look like y minus f of a equals f prime of a x minus a. When we're using a tangent line to find an approximation of a value on the curve, we might want to rearrange the terms of the tangent line equation to write y equals f of a plus f prime of a x minus a. This just makes it look nicer, so we're solving for y instead of having to flip things around after the fact. It says, note, y represents the y-coordinate of a on the tangent line. This gives us an approximation of f of a. The y-coordinate of a on the function f of x is represented by f of a. F of a is the actual value. Okay, so I get asked this question a lot, and basically, what's the point of doing these approximations? Well, back in the day when you didn't have calculators and it was a pain to calculate exact values, say you had some really nasty equation. Instead of calculating all of those values for that equation, what you could do is you could simply, in this case, use the tangent line to approximate what that value was. Now, so long as you were, ballpark within, a couple thousandths or so, it wouldn't really matter how off the approximation was. And so it was easier and much faster to approximate those values than to actually calculate them by hand. So for starters, we're going to do a pretty easy example just so that you can kind of see how this works. So we're going to start off with f of x is equal to x squared. So it says, write the equation of a tangent line to f at x equal 1. Use your answer to a to find an approximation for f of 1.01, and then find the actual value of f of 1.01, and then find the amount of error of your approximation. So let's consider what we're talking about up here and how these numbers fit into the whole picture. So our f of x is x squared. It says to write an equation for the tangent line of f at 1. Now the question is, why are we choosing 1? Well, the actual value that we're trying to approximate is 1.01. So with linear approximation, what you want to do is you always want to choose a value that's really, really close to the value you're trying to approximate. So in this case, we're trying to approximate this. So something really, really close that's easy to find x squared of is something like 1, because 1 is right on the left side of 1.01, and it's super easy to calculate in this guy. So what we're going to do here is we're going to use 1, and we're going to use the tangent line at x equal 1 to approximate this value 1.01. So let's start off with answering question A. It says write the equation of a tangent line at x equal 1. Now, for part A, write the equation of a tangent line. So the equation of a tangent line is y minus y1 equals m times x minus x1 whenever we write it in point slope form, right? So let's think about what we're going to need. We're going to need some point x1, y1, and we're going to need some slope. So the slope of that tangent line at x equal 1 is just going to be the derivative f prime of x at x equal 1. So let's start off by finding out what those values are. So we know that f prime of x, the derivative of x, is equal to 2x, and this gives us our slope of this tangent line. So in other words, this is what the slope is. However, we're looking for the value at x equal 1. So f prime of 1 is equal to 2 times 1, which is just 2. So our slope m is equal to 2. Now we need to figure out these values, x1, y1. Well, we know what x1 is. x1 is 1. However, how do we find y1? Well, f of 1 is equal to, and now notice this is f of 1, so we're going to plug it into f of x is equal to 1 squared, which is just 1. In other words, we're looking at the point 1, 1, right? So far we have x1, y1, m. So we're pretty much ready to plug this into here. Now let's go ahead and rewrite it this way. So this said y is equal to f of a plus f prime of a times x minus a. Now y is equal to, we know that f of a is 1 plus f prime of a is 2 parentheses x minus a, and a in this case is 1, so x minus 1. If you distribute everything out and add things up, you get y is equal to 2x minus 1. So that is the equation of the tangent line of f at x equal 1. Now in question B, or in part B, they say use your answer to A to find an approximation for f of 1.01. Now this is what we were saying up here. It says that we can use the equation of the tangent line. Oh, you can't see it. You can use the tangent line to find the approximation of the value on the curve. So the point of finding out what y equals 2x minus 1 is so that we can approximate now what the value of 1.01 is. So we're going to plug in 1.01 into our y equals. So y equals 2 times 1.01 minus 1. So you get y is equal to 2.02 minus 1. So y is equal to y is equal to 1.02. Okay. All right. Now it says to calculate the actual value of 1.01, f of 1.01. So what we're talking about is f of 1.01, which is equal to 1.01 squared. So if we plug this into our calculator, or if you actually calculate it out, 1.01 times 1.01, you get 1.0201 exactly. Okay. So then let's do the last one. The last one says to find the amount of error in your approximation. So let's look at the values. This is our approximation. That's our approximation. What the exact value was is this. So we're not off by much. We're off by 0.0001, right? So a 10,000th of a decimal is what we're off by, right? So let's look at what our percent error is. So percent error, if you think back to science, percent error is equal to the absolute value of your approximate minus the exact divided by the exact value times 100. So if we plug in our values in, our approximate was 1.02 minus 1.0201 divided by 1.0201 times 100. We calculate that error and we get 0.009% error. So when you're thinking about percentages, that's actually not that bad. That's I mean, your 9,000ths of a percent off from 1.0201, we got 1.02. Okay. Let's do another one. Okay, this one's particularly useful. Because see, and here we can kind of see a more practical application of why we would use this approximation. It says use a tangent line approximation to approximate the value of the cube root of 127. To do this, let f of x equal the cube root of x. So our function f of x is the cube root of x. And then choose a perfect cube close to 127 and build your tangent line at that value. Now, here the key is to pick a value that's really close, like I said before, to the value that you're trying to approximate. And so a perfect cube that's really close to 127 would be 125. Okay. Now, let's just follow the same exact process as before. So in part A, we wanted to find the equation of the tangent line. So the first thing we found was what f prime of x is. And if f of x is the cube root of x, that means f prime of x, well, let's also rewrite this as f of x is equal to x to the 1/3 power, right? That means that this is 1 over 3 times x squared, I believe. No, not squared, 2/3. Because you subtract 1 from 1/3, so then you bring the 1/3 down, that's where the 1/3 comes, to the x to the negative 2/3, which is why we have 2/3 on the bottom. Okay, so that's what f prime of x is equal to. Now, we needed to know what the slope was. If we're using 125 as our approximation value, then we're going to say f prime of 125 is equal to 1 over 3 times 125 squared and then cube rooted, because that's what that means, right? So the easiest one to do here is to take the cube root first. So the cube root of 125 is 5. So this is equal to 1 over 3 times 5 squared. 5 squared is 25 times 3 is 75. So this is equal to 1 over 75. Okay. Now, the other thing we need to know is what f of a is. So if a is equal to 125, then that means that f of a has to be equal to the cube root of 125, which is equal to 5. So we have a point at 125, 5. Okay. Okay. So we have our slope, we have our point, a and f of a. So let's plug it into our formula again. That was y equals f of a plus f prime of a times x minus a. So that means that y is equal to f of a is 5 plus f prime of a is 1 over 75 and x minus 125. Now the next step, I recommend you take a moment to kind of try and figure out what I did. But basically, I'm going to distribute and then find a common denominator between everything. And so we'll get y is equal to x plus 250 over 75. So once again, all I did here was I distributed well, you don't even need to distribute really. It's just x minus 125 over 75. Find a common denominator, so multiply 5 by 25 over 25, combine them, and you should get x plus 250 over 75. Now the reason I did this is because this is just going to be a lot easier to plug into your calculator later whenever you approximate these. Okay, so this is your equation of a tangent line. So let's go back up here for part B. And so in part B, if you recall in the previous step, in part B we used the equation of the tangent line to approximate our value at the value we're trying to approximate. So in this case we're trying to approximate 127, right? And so for B we're going to say y is equal to 127 plus 250 divided by 75. So you plug this into the calculator and you're going to get something like y is approximately 5.0266, and it's technically 66 repeating. Okay. So that's what we get. Next part C, if you recall, was to calculate the actual value. So f of 127 is equal to the cube root of 127. And if you solve for that, you should get 5.02653 and so on, right? But I'm just going to write these numbers for now, just so we don't have the never-ending decimal. Okay, so we get that. Now part D was to calculate and was to calculate the error. So let's look at the difference between these two. This is 6666666. So we're off by 0.0007-ish from what we wrote. That's not bad. That's smaller than the previous problem. So let's just calculate to see what the percent error comes out to be. So if you do part D was your percent error, which was equal to, we said, the absolute value of the approximate minus the exact divided by the exact times 100. So here's our approximate. Here's our exact. Okay. And so when we plug this all in, we have 5.02666 minus 5.02653 divided by... Now bear in mind, when you're plugging these into the calculators, it would be a good idea to store these values into a variable of some sort, and then use them in this formula so that you can get a more precise error. Because if you start truncating or rounding numbers off, your error is going to be off. Divided by 5.02653 and so on, right? Times 100. And when you calculate all of that out, you should get something about 0.002% error. Okay, which is a lot better than in the previous one. Now, the reason for that, in this case, I guess our 127 approximation is a lot closer to 127. Yeah, 125 to 127 is a lot closer than 1.01 to 1, which is strange when you think about it. But if you really sit down and think about it, you're talking about a cube root, right? So the difference between these two in a cube root is pretty small. So that's how you do linear approximation. All right, guys, let's talk now about differentials. So this section shouldn't be too bad. So let's talk real quick. It says, this is taken from the Finney textbook. It says, now a lot of you have probably seen the Liebniz notation, and it's kind of confusing, and sometimes it makes sense, sometimes it doesn't make sense, and this kind of explains why that's the case. It says the Leibniz used the notation dy over dx to represent the derivative of y with respect to x. The notation looks like a quotient of real numbers, but it is really a limit of quotients in which both numerator and denominator go to 0 without actually equaling 0. So they're limits, so to speak. Leibniz did most of his calculus using dy and dx as separate entities, but he never quite settled the issue of what they were. So that explains why they're confusing, because he never really explained what the heck they meant. To him, they were infinitesimals, non-zero numbers, but infinitesimally small. So really, really small numbers, but numbers nonetheless. This is why when you do things like implicit differentiation, something like a dx over dx cancels out, because it's essentially a really small number over itself, right? And so it cancels out. It says it is tricky to define dy and dx as separate entities, but since we really only need to define dy and dx as formal variables, textbooks define them in terms of each other so that their quotient must be the derivative. So this is why we see them as dy dx whenever we take a derivative. It says let y equal f of x be a differentiable function. The differential dx is an independent variable. The differential dy is dy equals f prime of x times dx. The variable dy is always a dependent variable. It depends on both x and dx. And that makes too much sense if you really stop to think about it, because if y is a dependent variable in something like y equals mx plus b, so in other words, y is dependent on x, it would make sense that the derivative, or the change in y, is dependent on both x and the derivative of x, or x and the change in x. Okay, so one way that'll really help you kind of understand what dy and dx really mean, dy is essentially the change in y, d stemming from delta. so delta y, change in y, right? And dx stemming from change in x, or delta x, right? So change in x. Now, it would make sense then that when you're talking about them as dy over dx, you're talking about the rate of change of y with respect to the rate of change of x. Okay, so this is why whenever we read these, we read them as the derivative of y with respect to x. And what it really is the rate of change of y with respect to the rate of change of x. Okay, so that's why these kind of make sense. And separately, we can treat them as the change in y and the change in x. Okay, so let's see how these are used. So let's start out with the first example. The first example says, find the differential dy given y is equal to f of x cubed. Now, one way that you can definitely do this is to just implicitly differentiate both sides. So if you differentiate this side, you get dy over dx is equal to, the derivative of this side is 15x squared dx over dx, right? If you think back to when you did implicit differentiation, technically there is a dx term because you're taking the derivative of an x term with respect to x, right? So that's where you get the dx over dx. And we said that these cancel out. But let's just look at this carefully now. If we treat this dy dx and this dx dx as a quotient, much like it says up here early on, where it says the notation looks like a quotient of real numbers, but it's a limit of quotients. If we treat it as quotients, or treat them as quotients, let's solve for dy. If we want to solve for dy, we multiply both sides by dx. Multiply both sides by dx. These cancel out, those cancel out. And what you're left with is dy is equal to 15x squared times dx. Okay, simple enough, right? So let's see how we can apply this to a problem like this. It says the radius of r of a circle increases from 10 meters to 10.1 meters. Now, before we start this, let me go back to say that we said dy over dx is equivalent to saying the change in y, dy is the change in y, and we can say that dx, is the change in x. Okay, so if dy is a change in y and dx is a change in x, let's look at this problem thinking of those pieces like that. It says use the differential dA to estimate the increase in the circle's area. Well, let's start out with a formula that we do know. A is equal to pi r squared for a circle, right? So if we take the derivative of both sides and we look for the differentials, we get dA is equal to power rule, so 2 pi r dr. Okay, so I just kind of skipped the step with the dA over dr and just threw it over to the side. Okay, so this says the change in the area is equal to 2 times pi times r times the change in the radius, if we read it the way we define these up here. Okay, so we know that the radius to begin with is 10. So r is equal to 10, right? If the radius increases from 10 to 10.1, then what's the change in the radius? Well, the change in the radius dr is equal to 0.1 meters, right? So that's where our dr comes from. We know what r is, we know what dr is, so now we can solve for dA, okay? So that means that dA has to be equal to 2 pi times 10 times 0.1. Now this is really nice because what's 1/10 of 10? Well, it's just 1. And so these cancel out, and you're left with the change in the area is equal to 2 pi meters squared, right? So let's look at part B. It says compare the estimate you found in A with the true change delta A and find the error in your approximation. Now, this one you really got to think. We have to figure out what the true change is, delta A. Well, delta A, and I'm going to write it a very specific way so you can understand what's happening here. Delta A is equal to A of R plus delta R, in other words, R plus the change in R, minus A times, A of R, right? So the area of the original radius, and then the area of the new radius, so new minus old, gives you your change in the area. So that means it's pi times 10.1 squared minus pi times 10 squared. This is equal to pi. We're going to factor out a pi, and then we're going to square these. So 10.01 is 102.01 minus 10 squared is 100. And the reason I'm doing this and not multiplying everything out, you'll see, that's a change in area. So the change in area is equal to 2.01 times pi. Now the reason I did it this way is so you can see what actually happens. In the actual calculation of the change in the area, you get 2.01 pi as opposed to our approximation, which said 2 pi. Okay, so we're off by this 0.01 factor, so to speak, right? So this is in the hundredths place. It's actually pretty significant, especially when you're multiplying it by pi. So let's look at the error in our approximation. So you have percent error is equal to, we said, approximate minus exact, and we're taking the absolute value of that, dividing it by the exact value, and then multiplying it by 100. So you have the approximate value, which is 2 pi, minus the exact value, which is 2.01 pi, over 2.01 pi. So the pi's all cancel out, and then we're left with 0.01 over 2.01 times 100. So this is a percent error of approximately 0.497%. So while the differential makes the calculation really, really quick, the approximation really, really quick, the error is pretty significant in terms of percent error, right? It's almost half of a percentage point off. Okay. There is another problem. It works very, very similar to the circle problem. Okay. I'll go ahead and pause the video for about 30 seconds for you to copy this down if you want. Okay. And give it a shot. Basically, you have the original radius. You know what the change in the radius is, okay? And so when we're looking for what the tolerance of that would have on, what effect that tolerance would have on the estimate of the surface area, you're looking for percent error, right? One thing that'll help you here is that the surface area of a sphere So the area of a sphere, we'll leave it at that, is equal to 4 pi r squared. Okay, so that kind of gives you a starting point for that problem. Thanks for watching, guys. See you next time.